Welcome to this Frequency Matters podcast. I'm Pat Hindle, and I'm talking with Matt Tyhach, Mission Area Director for Next Gen Sensors and Microelectronics in the Advanced Technology at Raytheon. Welcome, Matt.
Hi, thanks, Pat. Thanks for having me.
So Raytheon's been working on GaN devices for decades. I've been following it. I used to actually work on some of the gallium arsenide programs, so I'm very familiar with it. And you were recently awarded a $15 million contract from DARPA to increase the electronic capability of RF sensors with high power density GaN transistors. So can you tell us a little bit about this award? What are some of the goals and timing of the project?
Yeah, I'd be happy to. So the program Threads is all about unlocking the power of GaN to operate in higher performance than the GaN that's today in production and being fielded in DoD systems. So what do I mean by that? So GaN today is really limited in power capability due to heat restrictions, due to thermal. So there have been papers published, many data points that have shown that GaN can operate at higher power densities. But the consequence of doing so is they generate too much heat. And that heat directly correlates to performance, specifically reliability. And in DoD systems, GaN and the resulting systems from GaN have to operate 30 years out in the field. So we cannot sacrifice reliability for performance. So what DARPA is doing, and we absolutely support it, is they're investing in ways to address that heat bottleneck in GaN through some new innovations. And the innovations are really all about how do I get the heat out of the GaN as fast as possible. And when we do that, we can now go back in and really generate more heat. So it's a self-licking ice cream cone there. So, for example, if today's GaN is, output power is 5 watts per millimeter, and the transistor is 50% efficient, that means it's also generating 5 watts per millimeter of heat, and that millimeter is the size of the device. So, through innovations in material selection, substrates, etc., we can get the heat out quicker and get higher power density. And in terms of timing, so we were just awarded the contract this November. It's a 48-month program. And the way DARPA MTO operates is there's multiple phases to each program. Phase 1 is 18 months, phase 2 is 18, phase 3 is 12. And throughout the program, there's a series of metrics that are tracked. And if each metric is effectively a graduation exercise to get from one phase to the next. The program itself is kicking off formally in a few weeks, and Raytheon and the other performers will have a chance to share our concepts together.
Sounds great. And I think you have many partners in this program, some universities and some other organizations. Can you tell us about those and what they bring to the table as far as expertise?
Yeah, absolutely. So it's a very challenging program. DARPA hard is the catchphrase, so we need a lot of great expertise from around the country. And we pulled in a lot of partners that we've been working with over the years. So Raytheon as the lead, we're responsible for the transistor design itself. We're manufacturing the transistors at our 3.5 foundry in Andover, Massachusetts. And we're also responsible for the reliability testing that I mentioned. It's a key metric on this program, making sure that indeed all the improvements are still creating a reliable device. NRL, or Naval Research Lab, is a key partner for us here. They have a lot of expertise with device development, semiconductor device development, as well as diamond growth. So one of the key aspects of this effort is integrating diamond into the transistor structure and the substrate. And NRL will be providing expertise with topside diamond growth. We also have Cornell University as a partner. They're helping with the intra-transistor device design with new materials, new layers, and how we model those to ensure that our development is guided by proper simulations and material characterization. We also have Stanford University. Their expertise is in topside diamond growth, specifically at lower temperatures. One unique aspect of diamond is typically the higher the temperature growth, the better the conductivity. But as you get higher, you start to damage your device. So we want to incorporate a lower temperature diamond growth that the device will still utilize for conductivity, but is still consistent with the processes that are needed to create that transistor. We also have two more universities, University of Maryland and Penn State University are helping on the thermal modeling and characterization aspect of the effort. So as you can imagine, we're going to model, we're going to fab, and then we're going to test. And we need to have expertise in all phases of that. So Maryland and Penn State will help with that. And then Michigan State University, our last academic partner, they have some very unique capabilities with phonon transport modeling. And this is really, at the atomic level, how heat is generated and moves throughout the device. And having a key understanding of that will help us engineer the structure of the transistor optimally for the program. And then our last partner is Diamond Foundry. They're a company that specializes in large diameter single crystal diamond wafers. So they'll be providing those for us as our substrate for the effort, and those will be bonded into the transistor. So a lot of great key partners here. Really looking forward to getting going on this program.
Definitely the A team. Sounds good. And so the goal of this program is to have improved transistors with 16 times higher output power than traditional GaN devices with no increase in operating temperature. How do you plan to accomplish this? What does the structure look like? And can you give us a general idea of the operating frequency?
Yeah, absolutely. So for the frequency question, DARPA has specified this should be a X band or 10 gigahertz, which is a typical radar frequency, typical frequency for radar operation. So as far as the structure and our approach, the first thing we need to do is create the thermal problem. So that means today's GaN device, while it's optimal for operating where we field it today, we need to increase the drain voltage, which means increasing the breakdown so that we can generate this 16 times higher power device. So we'll be engineering certain geometries and spacings on a transistor, things like gate dimensions, source drain spacings, field plates, that'll allow us to take today's breakdown voltage and increasing it significantly. So once that's done, then we start addressing the thermal. And we need to throw the kitchen sink at this. There's many tools in our tool belt to do so. I've mentioned diamond a few times here. So extrinsic to the device itself, so we're using diamond on both the top side and the bottom side. So the top side will be accomplished through low temperature growth on the surface of the transistor. And on the bottom will be the bulk diamond from Diamond Foundry that'll be bonded to the backside of the transistor using a very thin, very low resistance bonding process. So between the two of those, they're effectively wicking the heat away using the world's highest performance material, which is diamond. Now, intrinsic to the device, there's other tricks we're doing to reduce the thermal resistance. One of those is addressing the GaN material itself. So when we grow GaN, it typically has a buffer in the material that allows the GaN to be matched to its host substrate. We're looking at techniques to thin that buffer. The thinner it is, the less resistive it is. And then there's other materials such as aluminum nitride, which offer higher thermal conductivity, which can replace a good portion of that GaN buffer. So between the intrinsic material selection and the extrinsic diamond, these are some of the key levers that will get us to that 16x performance.
So I do remember quite a few years ago, DARPA did have a program for GaN on diamond. I think like Element 6 was doing the substrates, and Qorvo, maybe the devices, Raytheon may have been involved then. So how is this different? It sounds like you're taking it to the next level.
Yeah, no, you're absolutely right. So we were part of that group. DARPA had two programs. One was near junction thermal transport, or NJTT, and the other one was interchip enhanced cooling, or ice cool. Raytheon and myself, we participated in all those. So you can consider those as really early investigations into this technology. At the time, the concept of improved thermal was known, but really not it was not demonstrated in a robust way. So some of the key outputs of those efforts were robust thermal modeling techniques. As I mentioned, modeling of different materials and layers require some pretty advanced techniques to accomplish correctly. And the second half of that was really measurement techniques. A lot of effort into how do we measure thermal performance of semiconductors was a key output from those two programs. And Raytheon did demonstrate GaN on diamond transistors with 3 to 5x the power density. But yeah, now we're going after 16x. So much more aggressive. Lots of lessons learned from those programs. One key one, those efforts use polycrystalline diamond, which does not have a specific grain or lattice. And as a result, the diamond performance is not as good as it could be. Now we're using single crystal diamond, and so we get the best connectivity possible. The other key lessons learned were in terms of the diamond preparation. In order to bond diamond, you need the surface to be very smooth. And a polycrystalline, the way the diamond grows, you can never achieve as smooth an interface as you need, because the way the grains grow, there's always pits or different features. With single crystal diamond, you can provide a much smoother surface to bond to. We are still working on the material coming out of NJTT and ice cool with Element 6, now Akash systems, and we're still following that technology, but certainly Threads is taking that 3 to 5x to 16 and that next degree of performance.
Well, plus you're putting diamond on the top to spread the heat, because, the active material is usually on the top. So I always thought, flip chipping was a good idea too, to try to dissipate the heat.
Exactly. So this is really a sandwich in a flip chip.
And so can you give us an idea of how the substrates will be produced and grown, and how the material will be attached to that and processed, just kind of in a general sense?
Yeah, absolutely. So as I mentioned, so Diamond Foundry is our partner on this effort. They are certainly in the lead in the marketplace for providing large diameter single crystal diamond. We surveyed and we've been working with them for some time, understanding their market and where they're headed, and they're part of our team here. So what's sort of unique about their capability is the size. Single crystal diamond is known in smaller diameters, maybe 10 millimeter squares. But in order to achieve the program goals and where we want to head, you really need a process that's consistent with the larger wafer diameters, 50, 100 millimeters, et cetera. So they are providing that. I also mentioned the bonding. So what's key here is to get that bond to the diamond as thin as possible, and the polishing of the diamond down to less than a nanometer of roughness is absolutely critical for this program.
And so what type of testing and evaluations will you do at the device and system level to verify it?
Yeah, absolutely. So DARPA has mandated all performers need to have a standard evaluation circuit, which in this case is a single stage MMIC that operates at X band. So this was a good selection because it exercises not just the transistor, but it exercises the full process to create a MMIC. So passives, the appropriate layers that you use in 3.5 Foundry. So it's a good vehicle that's representative of what it would take to take this technology to the next level in maturity. So we will have some of our standard electrical testing that we do day to day on our circuits and transistors. So things like IV curves, RF load pull at X band on both the transistors and the circuits. And then on the thermal side, because as I mentioned, NJTT and ice cool created the foundation for thermal measurement techniques. we'll be using things like steady state thermoreflectance and time domain thermoreflectance. These will help us characterize the different planes of the diamond to ensure that our models and measurements are correlated well. Gate resistance thermometry and Raman will also be used to measure the diamond itself and the surface of the transistor, so we can see as close to that hot spot as possible in our transistor. And once again, all those measurement data will go back into our models, and we'll learn and improve our device as each phase of the program evolves.
And I imagine there'll be reliability testing too.
Oh, absolutely. Yes, absolutely. There's a reliability requirement or a robustness metric that we need to meet, and we will be doing that as well at Raytheon.
And so GaN improves the range and radar resource management handling of radar, and Raytheon performs as prototyping under the DARPA technologies for heat removal and electronics and the device scale program, which you already mentioned, known as THREADS. How does this program help in this area specifically?
Yeah, so at Raytheon, we're always thinking about where these technologies head and how we can transition them into systems. So GaN itself has been in production for many years, and it's enabled a new class of radars that we refer to as software-defined apertures. So what this means really is, a radar is not just a radar. A radar can now be an EW system. It can now be a comms system. It's really all about flexibility. So we can, change missions on the fly. We can tailor performance real time as the mission evolves or changes. And what GaN does, it allows us that flexibility to change from, say, a high voltage saturated amplifier to a lower voltage linear waveform for communications. And so where THREADS comes in, from this perspective, is that it really adds more flexibility, more capability. So we can do more radar missions, more EW missions, more comms missions. We'll have more dynamic range between, say, a radar mode and a comms mode, for example.
And so how do you see this affecting the overall architecture of systems in the future? How do you see things evolving with these advancements?
Yeah, no, great question. And this is our primary interest as being a partner on this THREADS effort. So expanding a little bit more beyond that software-defined aperture story. So there's some obvious examples of where higher power GaN could have a role in the market. The first one of those, we're seeing legacy systems that use vacuum tubes for transmitters. The benefit of vacuum tubes is they generate very high RF powers, kilowatts of power. The downside is they fail very frequently, and they're expensive to replace. So we've been looking at how do we do gallium nitride or GaN versions of these solid state transmitters that would replace these tubes. And we achieve that by combining many amplifiers together. So if we can instead use this THREADS device, we'll achieve the same power densities as tubes, but with less combining, much less combining, which means more efficiency at the system level, more affordable solutions, and having a solid state versus a tube just means a more a lower cost sustainability story for the warfighters. Another paradigm we're looking at, many of systems are limited in aperture size, particularly airborne sensors. You can only have so big of an antenna on a plane, for example. So there's situations where you want more RF power, but you just physically cannot create it on that platform. So we see higher power density, meaning more range, more sensitivity, more flexibility for these multi-mission apertures on these platforms. The last, on the radar side, having higher power density also gives us a new knob in how we can design radars. So typically there's several degrees of freedom, power per element, size of the aperture, cost, and we all trade these and try to find the right bucket curves to meet the requirements. Having a new knob of more power per aperture is something we have not yet explored fully, but I I believe it'll be very beneficial to these systems. And then lastly, there's systems out there we just haven't thought about. And this really unlocks that potential to go explore new mission areas, talk to our customers about where they need higher power density with their soldiers.
Well, very exciting project, Matt. Look forward to what comes out of it. We'd love to follow your progress. And as you have any updates or results, it'd be great to have you back once in a while. But thanks for talking with me today about the improvements in GaN technology for your systems.
Absolutely. Thank you so much for having us.
To our listeners, you can find more podcasts at podcast.microwavejournal.com. Thanks for listening.